record. We'll be playing with, let's see, color rods today. Let's open that up. Let's see, color tiles, maybe, maybe not. We have somebody, another guest. Let's see, where are my guests? Mason, welcome Mason. Glad you could join us. We're just getting warmed up here. The reading assignment I still need to grade. I totally spaced that out last week. Big surprise, sorry. We're gonna work on the activity some more today. Hopefully you did a little bit of work on it. I realized when I was playing in the last class with the document camera to show the toys that I didn't have Zoom set up right to do that, and the video came out looking really crazy. So I made a new video after class. And oh, somebody else mentioned they were having trouble finding videos. So let's see. This needs updated. I decided to add a new playlist for this quarter in particular. So these are videos from the last quarter, which covers the same stuff. And the syllabus must have the link to the, maybe, what's the question mark there for? Let's check it out. Sorry, too many classes, too many days. This is, that's the 2021. And then at the moment, new videos are ending up in the bottom here. So these last four were from last week. And okay, so apparently I just thought about making a new playlist for 2021 and haven't actually got to it yet. But I think I'm probably going to do that. All right, so at the moment though, videos go here. YouTube changed the way they do business on me. It used to be if I had like Math 2, MTH 212 or MfEST 2 in the title, it would automatically stick it in the playlist, but they got rid of that automatic add feature. So I have to upload them, and then after they upload, I have to remember to put them in the right playlist. So if a video is missing, send me a note saying, Parker, where the heck's this video? And that means I forgot to push an extra set of buttons. My apologies, I can't push all the buttons at the same time. I have to, there's like a time lag of like a half an hour in between upload and when I can categorize them. All right, anyway, that's kind of boring stuff. Let's do some math. So we need...
Harry?
Yo, what's up?
This
Oops, hello, I lost you there.
on the grading like assignment thing, it says
Yeah.
activity 6.1 is due February 12th of 2020.
Oh, darn. It could be because the way I migrated the course from last year, I still have to move some dates around. You said it was activity 6.1?
Yeah.
Okay, I'll double check that and fix it. Yeah, so we have to finish chapter 4 and then chapter 5, and then we'll be in chapter 6, which is decimals. I thought I had fixed all the 2020 versus 2021 date issues, but apparently not. Thank you for pointing that out. Hey, are there other questions or comments before I start rambling on about math that we need to get done?
I have a quick question. Can you hear me this week?
I can. Hey, Amanda, you sound better this week. Good job.
Thank you. I don't know. And it's really a stupid question, but on the homework 4.1 on question 13, and it's nothing to do with solving it, but I'm not sure how to answer it. Okay, that's a,
I wonder if that's like the same one somebody else brought up to me. Let's take a look right now. Number 13.
Yeah.
Let's see. Yeah, this is the one I rewrote. So, it doesn't make it completely clear, but I wanted to go over these color rods last week and I didn't get to. We're gonna go over using them today. They're called color rods or color strips or Cuisenaire rods. They go by different names, but they're common in elementary classrooms. So here I want to write a divisibility statement based on the color strips below where orange is 10. So I'm just going to scribble on this in my notebook. Let's see, can I get all of it? Let's try that again. There we go. Okay. So what that implies here, what a divisibility statement is the mathematical version of a divisibility statement. So, uh-oh, my battery is low. Oh boy, better fix that. So this is worth 10, and I can see above here that the red is worth 2, so I have 5 groups of 2 here. And so I think, and I could be wrong, the most natural one is to say that, oh, well, this means that 2 divides 10. So that's a divisibility statement in words. The math version of that would be 2 vertical bar 10. And so that's what I was looking for here. Now, somebody else might look at this and say, well, there's 5 groups of 2, so doesn't this also tell us that 5 divides 10? And yeah, it tells us that too. And so originally I was only taking this first answer over here as the correct answer, but I decided that this other perspective is fine too, that 5 divides 10.
How do you enter the vertical bar? I know that's probably a stupid question.
It's on your keyboard above enter. So above enter or return on your keyboard should be a backslash, and above, if you do shift backslash, that gives you the vertical bar.
Yeah, that took me a bit. I messed up a couple times, and I was like, what am I doing?
I drew it on the screen, but I totally forgot to tell you guys where is it on the keyboard. So I could either enter 2, the vertical bar is shift and then backslash on my keyboard, and then 10. So that should be one acceptable answer for this one. And then I also added to accept 5 divides 10. Yeah, so it's the vertical bar on the keyboard, which is above enter with a shift. Yeah, and that's the same question I got emailed. And prior to this morning, this picture of the color rods wasn't there. I probably should make it more clear about the divisibility statement. So I'll have to think about how to clarify that part.
Could we also go over, I just wanted to look at 14 again and make sure I'm doing it correctly.
Yeah, sure. Yeah. So is question 13 clear? Does anybody have another question about that one, or are we okay? We're okay. All right, 14, let's take a look. All right, illustrate and explain this divisibility statement using the following 2 models. Yeah, so if you look in your book, the book talks about the linear divisibility model, which is either a number line or those color rods, versus the rectangular divisibility model. So let us, yeah, so this is something I was going to go over today. Let's get a screenshot. And we've still got quite a bit of work to do to finish, oops, wrong page, section 4. And we have some chats going on. Okay, and Lauren had a question about number 14 too. All right, so mine says 9 divides 27, so I want to just illustrate this in a couple of ways. So how can I show that 9, oops, it's a lousy 9 divides 27. So the linear divisibility model, so these numbers are too big for the color rods, but I could just draw out a number line to do that. And that's probably way bigger than I need, but that's okay. And then let's mark this off. Let's say that much is 9. So, oops. So here's a 9, and then another 3, there's another 9, so that would be 18, and then another 3 is 27 there. And so here I have a group of 9, and another group of 9, and another group of 9 to make 27. So this is part A. There are 3 9s in 27. So here's my illustration right here on the number line, and here's my brief explanation of why 9 divides 27. So that's linear divisibility. And again, you can use the color rods if the numbers fit, or you could just draw it out on a number line. B, the rectangular divisibility model, that's what we were working on in the beginning of the activity. So can I make a rectangle that shows 27 and 9 together, justifying the divisibility? Well, I know that 9 divides 27 since 9 times 3 is 27. And so I want to draw that as a rectangle. So using the area model that we talked about last quarter. Rectangle, there we go. So this one I'll actually draw to scale. So 3 that way, and 1, 2, 3, 4, 5, 6, 7, 8, 9. I think I got that right. So this right here should be my 9 by 3. So let me just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So here is my 3 by 9 grid, and there are 27 squares within. And that's it. So illustration is just a number line or the color rods with your numbers. Illustration over here is just a rectangle showing the 9 and the 27 as the area. Does that make more sense?
Thank you.
Yep, you're welcome. All right, so let's, I just want to take a look at the color rods here. So I'm going to attempt to switch cameras. Give me a sec. I think I need a big desk for this. Let me see, I need to turn speaker view on. That was the mistake I made last time. And change cameras. Okay, oh, and I gotta turn off that crazy background. Sometimes technology is wonderful, sometimes it's such a pain. Too many buttons and too many places. Okay, that's a little bit better. So we played around with the color squares last time. I've got a new box of toys hiding underneath. These are color rods, color strips, Cuisenaire rods. So here I've got them organized kind of neatly. We have our 1 here, and our 2 are red, and our 3 light green, and our 4 purple, 5 is yellow, 6 is dark green. That's next. Black, 7. Brown is 8. Blue is 9. And orange is 10. And so often when I'm using these with people or children that are learning some kind of math concept, I like to have a set of them out in order like this. And like in that homework problem, I had them labeled 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There's my color rods. And then, you know, we could do things. I don't know if I have room on this table. Like, could I show the 3 9s for 27, or am I going to run out of room? Yeah, so this blue one is a 9. And I did not bring a good pen for this. Is that showing up backwards or forwards for you guys? Does it look like 9s? Or is it
It's showing right on my end.
right. Okay, on my screen it's a mirror image. It's freaking me out. All right, so there's my 9, 9, and 9 for the total of 27, right? So there's a kind of a toy version of it. And the rods are used a lot for multiplication, division, addition, subtraction, with smaller numbers for kids to get a physical idea of what's going on. And having this key there, I think, is always pretty helpful. Some kids just remember which color is which. Other kids need to look like me and count. Let's see, what is the dark green again? I forget. 1, 2, 3, 4, 5, 6. Oh, the dark green is 6, right. So I could play around with a dark green and some reds And so I can see that there's 2 groups of 3 in 6 when I put that together. And we're not together in a room, but I tried to mention last week how important it is that, you know, we are very visual beings. We interact with the world around us through sight and touch. And a lot of us struggle with mathematics. And there's some research that shows that the more physical you get building stuff mathematically, the better your brain is at processing mathematical ideas in general. So whenever possible, I like to introduce toys or ways that we can get physical with mathematics. And so here's a way we can do divisibility and multiples and factors with a set of toys. Switch back to my screen here. And alternatively, since, you know, I can't easily give you guys a box of these right now, on the resources page, I did link out to one of many online color rod color strip toys. Let's blow this up a little bit. And here they're giving me a problem to do, but I don't really need their problem. I can just do my own thing. Like a minute ago, I was showing that that's 6, and that's also 3 groups of 2. So we can see that 2 is a factor of 6, and 3 is a factor of 6. So we get both of those facts out of that. Alternatively, we can see that there's 3 groups of 2 in 6 between the light green and the dark green, the 2 groups of 3. So 3 is a factor of 6 and 2 is a factor of 6. So we have a couple of different ways we can illustrate that with these toys. And so to help kids get a better grasp on factor and multiple. So in either of these cases here, the factor is the smaller one, the multiple is the bigger one. And if we connect that to some mathematical notation, we're saying that there are 2 groups of 3 to make 6, right? That's the mathematical version of that toy there. Let's go bring a picture of that toy in here. That's the one I wrote. And just some things to note, the 2 and the 3 here are known as factors. Factors are things you multiply, numbers we multiply. The result, the 6 here, is often called the product. And the product is a multiple of other numbers. Some things we didn't talk about in too much depth last time was how do we find all the factors of a number? How do we find multiples of a number? And the multiples one actually is a little bit easier than the factors. And that was part of the point of the activity that we started. So in the activity 1 we worked on last week, we were looking at rectangles. Of squares. And so if I took a look at, let's blow this up a little bit. A rectangle that's made up of 6 squares here. It is 2 by 3. So again, so this is the rectangular model for factors and multiples. The previous one was the linear model for factors and multiples. 2 by 3 grid gives us those 6 squares there. And so this tells me 2 and 3 are factors of 6. And then the question was, well, what other rectangles can we make? And we probably played around and made a rectangle that looked like this one right here. So I could make a 6 by 1 rectangle. All right, so 6 times 1 equals 6. And I also could make a vertical version of that. And so this one right here, oops, I'm missing a digit there, 1 by 6. So this one tells me that 1 times 6. So 1 and 6. So somebody might say, well, this first one here and that, the second one here and that third one, they're really the same. And the answer is no, they're not actually. This one is long and flat. This one is tall. And did I miss one? 1, 2, 3, 4, 5. Oops, let's draw that up here. All right, so now it's 6 tall. They are different. So there are 3 different rectangles. Made from 6 blocks or 6 squares. Now, it also turns out 6 has, oh, I missed one. What did I miss? I lied.
The 2 and 3.
Yeah, the 2 and 3 can be switched. So I'm missing that one. Let's draw that over here where I have some more space. So there'd be 1, 2, 3. So I could have a 2 by 3 that shows, let's see, that one should have been 3 by 2. Usually like to write base and height second. So we have 4 different rectangles made from 6 squares. And if I take a look at all those different numbers, we have 1 goes into 6, we have 2 goes into 6, we have 3 goes into 6, and 6 goes into itself. So this right here gives me the factors of 6. 6 has 4 different factors. Now, we talked a little bit about these factors last time. There's different ways to categorize factors. One way we talked about before with the idea of proper factors. And proper factors are less than the number itself. So based on that, I can say the proper factors of 6 are 1, 2, and 3. So we have factors, which a number is a factor of itself, because with division, we end up with no remainder. And that was one of our definitions for what it meant to be a factor. You carry out division and there's no remainder. Proper factors have to be less than number itself, so 6 only has a few proper factors. Another way to categorize factors that I mentioned briefly last week, but didn't talk about in great detail, prime factors, and we'll spend more time on this today. So prime factors are factors that are prime numbers. So a prime number has exactly 2 different factors. So 6 is not prime because 6 had 4 different factors. If we pick on one of its factors, like 3, and we take 3 blocks, 1, 3 squares, 2, 3. So that's one way I could make a rectangle with 3, a 3 by 1, but I could also make a 1 by 3. So there's 2 distinct rectangles that represent the 2 distinct factors. So 1 and 3 are the only factors of 3. So 3 is a prime number. Now, usually when we're talking about prime numbers, we're talking about counting numbers because we're looking at divisibility, and 0 is kind of a problem with divisibility. So 0 usually isn't part of the discussion with prime numbers. 1 is, and 1 is a bit of a problem. If we take a look at the number 1, right, we have 1 square. There's not much I can do. I just have that 1 square. It's a rectangle also, and if I rotate it, it's still that same 1 square. It's 1 by 1. So, okay, I could write 1 times 1 equals 1. So these two are factors, right? Things we multiply are factors. And 1 is also the product. So this is getting weird. Because in all the other examples we looked at, we had 3 different numbers going on, right? We go back here, we have 3 times 2 is 6. We have 1 times 6 is 6. Okay, we had 2 numbers going on there that matched, but usually it was 3. 1 makes some weird stuff happen when we're doing multiplication. 1 is not prime because I don't have 2 different factors, okay? I only have a 1 and another 1. They're not different, they're 1. Another thing 1 is trouble with is the idea of proper factors. Proper factors are less than the number, so 1 has no proper factors because its only factors are itself, and that's not less than itself. So 1 is just weird, okay? Problem with 1 is its own factor and multiple. Nothing more. So the number 1 is special. It's very special in the world of counting numbers. It's very special with multiplication and division. When we multiply by 1, not much happens, right? 1 times 3 is 3. The 3 stayed the same. The 1 kind of vanished. If a number isn't prime, there's a couple of options. It could be 1. 1's not prime. And then another type of number we play with are composite. And the word composite just means made of other things. Like concrete is composite. It's made up of lime, it's made up of sand, it's made up of carbon, a few other things. A lot of the things we deal with are composites. Water is a composite made up of a couple of elements. The composites that we're talking about here with composite numbers are numbers like 6, which equals 2 times 3. 6 is made up of two prime numbers. So it's a composite number. 1, however, is not made up of prime numbers. It's just 1, so it's neither prime nor composite. So as far as counting numbers are concerned, based on the idea of prime, that gives us actually 3 categories. 1 is all by itself. Then we have prime numbers, and then we have composite numbers. So 1 is its own set. It's not prime, it's not composite. Primes are numbers like 2, 3, 5, 7. What's the next prime? Anyone? Let's see, chat disappeared. Come here, chat. There you are, 11. Thank you, Jimmy. Yeah, 11 would be the next one. And composite is any counting number that's not prime and bigger than 1. So 2, 3, what are we missing? 4, 6, 8, 9, 10, 12, and then there's a whole bunch of them. So we're going to look at some other relationships between primes, composites, factors, and multiples. Questions about prime numbers or composite at the moment?